This video is a recital of Chapter 4, Carbon and its Compounds. In the last chapter, we came to know many compounds of importance to us. In this chapter, we will study about some more interesting compounds and their properties. Also, we shall be learning about carbon, an element which is of immense significance to us in both its elemental form and its in the combined form. Activity 4.1. Make a list of 10 things you have used or consumed since the morning. Compile this list with the list made by your classmates and then sort the items into the adjacent table. If there are items which are made up of more than one material, put them into both the relevant columns of the table. Look at the items that come in the last column of the above table filled by you. Your teacher will be able to tell you that most of them are made up of compounds of carbon. Can you think of a method to test this? What would be the product if a compound containing carbon is burnt? Do you know of any test to confirm this? Food, clothes, medicines, books, or many of the things that you listed are all based on this versatile element, carbon. In addition, all living structures are carbon based. The amount of carbon present in the Earth's crust and in the atmosphere is quite meager. The Earth's crust has only 0.02% carbon in the form of minerals like carbonates, hydrogen carbonates, coal, and petroleum. And the atmosphere has 0.03% of carbon dioxide. In spite of this small amount of carbon available in nature, the importance of carbon seems to be immense. In this chapter, we will know about the properties of carbon which make carbon so important to us. Bonding in carbon, the covalent bond. In the previous chapter, we have studied the properties of ionic compounds. We saw that ionic compounds have high melting point and boiling points and conduct electricity in solutions or in the molten state. We also saw how the nature of bonding in ionic compounds explains these properties. Let us now study the properties of some carbon compounds. Most carbon compounds are poor conductors of electricity, as we have seen in table chapter 2. From the data given in table 4.1 on the boiling and melting points of carbon compounds, we find that these compounds have low melting and boiling points as compared to ionic compounds. Chapter 3. We can conclude that the forces of attraction between the molecules are not very strong, since these compounds are largely non-conductors of electricity. We can conclude that the bonding in these compounds does not give rise to any ions. Table 4.1. Melting points and boiling points of some compounds of carbon. Compound acetic acid, melting point 290 Kelvin, boiling point 391 Kelvin. Chloroform, melting point 209 Kelvin, boiling point 334 Kelvin. Ethanol, melting point 156 Kelvin, boiling point 351 Kelvin. Methane, 90 Kelvin, and boiling point 111 Kelvin. In class 9, we learned about the combining capacity of various elements and how it depends on the number of valence electrons. Let us now look at the electronic configuration of carbon. The atomic number of carbon is 6. What would be the distribution of electrons in various shells of carbon? How many valence electrons will carbon have? We know that the reactivity of elements is explained as their tendency to attain a completely filled outer shell, that is, attain noble gas configuration. Elements forming ionic compounds achieve this by either gaining or losing electrons from the outermost shell. In the case of carbon, it has 4 electrons in its outermost shell and needs to gain or lose 4 electrons to attain noble gas configuration. If it were to gain or lose electrons, it could gain 4 electrons from it can gain 4 electrons forming C4 minus anion, but it would be difficult for the nucleus with 6 protons to hold on to 10 electrons. That is 4 extra electrons. It could lose 4 electrons forming C4 plus cation, but it would require a large amount of energy to remove 4 electrons, leaving behind a carbon cation with 6 protons in its nucleus holding on to just 2 electrons. Carbon overcomes this problem by sharing its valence electrons with other atoms of carbon or with atoms of other elements. Not just carbon, but many other elements form molecules by sharing electrons in this manner. The shared electrons belong to the outermost shell of both the atoms and lead to both atoms attaining the noble gas configuration. Before going on to compounds of carbon, let us look at some simple molecules formed by the sharing of valence electrons. The simplest molecule formed in this manner is that of hydrogen. As you have learned earlier, the atomic number of hydrogen is 1. Hence, hydrogen has 1 electron in its K shell and it requires 1 electron to fill the K shell. So, 2 hydrogen electrons share their electrons to form a molecule of H2 hydrogen. This allows each hydrogen atom to attain electronic configuration of the nearest noble gas, helium, which has 2 electrons in its K shell. We can depict this using dots or crosses to represent valence electrons. The shared pair of electrons is said to constitute a single covalent bond between the two hydrogen atoms. A single covalent bond is also represented by a line between the two atoms as shown in the figure 4.2. The atomic number of chlorine is 17. What would be its electronic configuration and its valency? Chlorine forms a diatomic molecule, Cl2. Can you draw the electronic dot structure for this molecule? Note that only the valence shell electrons need to be depicted. In the case of oxygen, we see the formation of a double bond between the two oxygen atoms. This is because an atom of oxygen has 6 electrons in its L shell. The atomic number of oxygen is 8 and it requires 2 more electrons to complete its octet. So, each atom of oxygen shares 2 electrons with another atom of oxygen to give us the structure shown in the figure 4.3. The 2 electrons contributed by each oxygen atom give rise to two shared pairs of electrons. This is said to constitute a double bond between the two atoms. Can you now depict a molecule of water showing the nature of bonding between one oxygen atom and two hydrogen atoms? Does the molecule have single bonds or double bonds? What would happen in the case of diatomic molecules of nitrogen? Nitrogen has the atomic number 7. What would be the electronic configuration and its combining capacity in order to attain an octet? Each nitrogen atom in a molecule of nitrogen contributes 3 electrons, giving rise to 3 shared pairs of electrons. This is said to constitute a triple bond between the two atoms. The electron dot structure of N2 and its triple bond can be depicted as shown in figure 4.4. A molecule of ammonia has the formula NH3. Can you draw the electron dot structure for the molecule showing how all the 4 atoms achieving noble gas configuration? Will the molecules have double, single or triple bonds? Let us now take a look at methane, which is a compound of carbon. Methane is widely used as a fuel and is a major component of biogas and compressed natural gas. It is also one of the simplest compounds formed by carbon. Methane has a formula of CH4. Hydrogen, as you know, has a valency of 1. Carbon is tetravalent because it has a valency of 4, or 4 valence electrons. In order to achieve noble gas configuration, carbon shares these electrons with 4 atoms of hydrogen, as shown in figure 4.5. Such bond, which are formed by sharing of electron pair between two atoms, are known as covalent bonds. Covalently bonded molecules are seen to have strong bonds within the molecule, but intermolecular forces are weak. This molecule gives this gives rise to the low melting and low boiling points of these compounds, since the electrons are shared between atoms and no charged particles are formed. Each covalent bond are generally poor conductors of Such covalent bonds compounds are generally poor conductors of electricity. Figure 4.5, electron dot structure of methane. Allotropes of carbon. The element carbon occurs in different forms in nature with widely varying physical properties, but diamond and graphite are formed by carbon atoms. The difference lies in the manner in which the carbon atoms are bonded to one another. In diamond, each carbon atom is bonded to four other carbon atoms, forming a rigid three-dimensional structure. In graphite, each carbon atom is bonded to three other carbon atoms in the same plane, giving a hexagonal array. One of these bonds is a double bond, and thus the valency of carbon is satisfied. Graphite structure is formed by the hexagonal arrays being placed in layer one above the other. Structure of diamond, structure of graphite, structure of C60, Buckminster fullerene. These two different structures result in diamond and graphite having very different physical properties, even though their chemical properties are the same. Diamond is the hardest substance known, while graphite is smooth and slippery. Graphite is also a very good conductor of electricity, unlike other non-metals that you studied in the previous chapter. Diamonds can be synthesized by projecting pure carbon to very high by subjecting pure carbon to very high pressure and temperature. These synthetic diamonds are small but are otherwise indistinguishable from natural diamonds. Fullerenes form another class of carbon allotropes. The first one to be identified was C60, which has carbon atoms arranged in the shape of a football. Since this looked like geodesic dome designed by the US architect Buckminster Fuller, the molecule was named fullerene.